Welcome. Let's take a look at creating some confidence intervals. So number one, suppose we know that the weight of standard poodles is normally distributed with a population standard deviation of 4.3 pounds. We take a random sample of 8 poodles and find their mean weight to be 52.4 pounds. Based on this sample, we'll construct and interpret a 99% confidence interval for the true mean weight of all standard poodles. All right, so the idea here is I'd like to know the mean weight of all standard poodles. But of course, gathering data from every single standard poodle in the world is not going to happen, not possible, not even realistic to try. So in inferential statistics, we use samples to try to estimate characteristics of an entire population. So we'd like to estimate the unknown population mean. So the best point estimate, so this will be the best single number that gets us started. So we'll do this in English first here. The best point estimate for the population mean is the sample mean. And then let's talk about our given values and symbols. So the first sentence says that the weights are normally distributed with a population standard deviation of 4.3 pounds. Now, population standard deviation, that should seem a little odd to know that information when I just said that we don't have data from all standard poodles of the world. So sometimes the population standard deviation will be provided to us, and then we're going to learn what to do when it's not. So when we write our given values here, that is sigma, population standard deviation. So we'll assume that's true since they said it. And then we'll move on to our sample. So N, sample of 8 poodles. And the mean weight of the 8 poodles came out to be, so sample mean X bar was 52.4. So that's our best point estimate for the population mean. And then we want our estimate to be done with 99% confidence. So just noting that. All right, so let's talk symbols then. So we're trying to estimate the population mean. And we'll always be asking ourselves if sigma has been provided. So we'll have 2 cases, one where they tell us sigma and one where they don't. So in this case, they did give us sigma, population standard deviation. So sigma is known, is what we'll say here. Sigma is known to us. So it's important to recognize from the very start here that standard deviation doesn't always mean sigma. It depends if it's population standard deviation or sample standard deviation. So we'll pay a lot of attention to that. So if we are estimating mu and population standard deviation is known, that's what allows us to use the Z distribution in our construction of our interval, and on our calculator, that will be our Z interval. And then we're ready to go to the calculator. So we'll hit stat, tests, and you'll go down to number 7. I usually just scroll to our Z interval. And then you want your input to be on stats. They did not give us the data for the 8 poodles. So we'll do some with data in a bit, but stats now, and enter your sigma 4.3 and X bar 52.4, N is 8, and then confidence level, we want 0.99, and calculate. And we're going to round to 1 decimal place, so lower limit there would be 48.5. And we're writing it in this form, so less than the parameter mu that we're estimating, and then the upper limit there would be 56.3. So let me go ahead and draw the picture of this interval. So 48.5 for the lower limit, and then 56.3 for the upper limit. And the point estimate would be in the center of the interval. So these intervals are symmetric about the point estimate, 52.4. So that value is your sample mean. That's called your best point estimate because it's a single point, a single number. And then the confidence interval is the range of plausible values where we believe the mean lies. So based on a sample of 8 standard poodles, so standard poodles are the larger poodles as opposed to my dog Chester. He's a miniature poodle, sort of the medium-sized ones, but this is our 8 standard poodles. We estimate with 99% confidence that the true population mean, so we'll learn to estimate other characteristics later. For now, we are estimating a mean, that parameter. So we think that the mean for all standard poodles, so the entire population of poodles, so based on these 8, we think that the mean is somewhere between 48.5, and the units up there were pounds, so between 48.5 pounds and 56.3 pounds. So we're quite confident that we're correct, 99%, but there is a possibility that this interval does not contain the mean. So we're never 100% sure if we don't collect data from our entire population. And that's just the nature of inferential statistics. So using samples to estimate parameters. All right. So let's switch it to what would happen if we wanted to keep all the information the same, but now I need an 80% confidence interval. So what if I don't need to be 99% sure that I'm right? I'm willing to just be 80% sure that my interval contains the mean. So we'll go back to stat tests, pick your Z interval. Everything else will remain the same except confidence level will change it to 0.8. And we see how that affects our interval. So now that lower limit is 50.5 less than mu less than 54.3. So it looks like I've got a smaller range of values than I did before. So we'll draw it here. So 50.5 to 54.3. The point estimate doesn't change. That was 52.4. All right, so what's happening here is I'm not as sure that I'm correct, but I'm giving a more accurate estimate, meaning a smaller range of values. So the margin of error in this example for 80% confident, so remember this distance to the ends, lower limit, upper limit, from the point estimate is our margin of error. So without even numerically finding it, I'm just getting the visual here that I've got a smaller margin of error than a 99% confidence interval. So I've got a smaller margin of error, but I am not as sure that I'm correct. So the way I think of it is like a target. If you give somebody a big target, they're more likely to hit it. Small target, people are less likely to hit it. So in the language of confidence intervals, I'm going to be less sure that the mean is in a confidence interval that has low confidence, as opposed to I'll be more sure, 99% confident, that the mean is in that interval because it's a bigger interval. So if you're asked to compare the lengths of these intervals, smaller confidence will always be smaller interval. So the 80% confidence interval is smaller since we have less of a chance that that interval contains our population mean as opposed to our long here 99% confidence interval. All right, so we'll see how that plays out in another example here. So number 2. Okay, so suppose that pizza delivery times in a delivery area are normally distributed with an unknown population mean and a population standard deviation of 6 minutes. So again, just a note here, it's sort of unusual to not know a population mean, but to know a population standard deviation. So we will address not knowing population standard deviation later. For now, we will go with this. So we have a random sample is taken of 20 deliveries, and that had a mean delivery time of 36 minutes. And we'll find a 90% confidence interval estimate for the true mean pizza delivery time in the area. All right, so given values here, so that population standard deviation is our sigma. So that's 6. And then they took a sample of 20 deliveries. And I'm just going to make a note here that they told us that the delivery times were normally distributed. That is required when our sample size is under 30. So we call this a small sample size. And there's this additional requirement to perform our confidence interval, and that is that the distribution is normal. So you're going to see some information that you don't necessarily use directly in your computations, but is necessary to meet conditions of the process. All right, so back to this. N is 20. All right, so for those 20 deliveries, the mean came out to be 36 minutes. So there's our sample mean. So X bar 36. And then we'll do a 90% confidence interval. So back to stat tests. I'm going to hit just number 7 now, so I don't have to scroll. There's my Z interval. And then we'll enter 6 for sigma, population standard deviation. Sample mean was 36. Our sample size was 20. And we're doing a 90% confidence interval, 0.9. And calculate, and we're going to round to a whole number here. So that will be a lower limit of 34 minutes. And we'll continue to write in our notation there, lower limit less than mu, population parameter, upper limit 38.2. So that would be 38 as a whole number. All right, so let's draw this. So 34, 38. Those are the lower and upper limits. And then I can see my point estimate there right in the, oops, sorry, at the lower limit there is 34. The upper limit's 38. Our point estimate is our 36. All right, so it's important to see here before we go forward that the interval is created based on a point estimate of 36. But when we write our answer, it's the symbol mu we're putting here because this is what we're estimating based on this information. So that's our confidence interval. So I can now say, based on a sample of, it was 20 delivery times, we could just say deliveries, based on a sample of 20 deliveries, we estimate with 90% confidence that the true mean pizza delivery time, and when I say true here, that's just another word for the population. So we could say both, true population mean. So based on these 20 deliveries, what I think is true for all pizza delivery times on average in the area is somewhere between 34 units per minutes. I'll just put it in the second value, 34 and 38 minutes. All right, so we want to compare that to, what if I want to be more sure my interval contains the mean? So basically, if I'd like to be more sure the interval contains the mean, I'm going to end up needing a bigger interval. So I'm going to need to give people more possible plausible values to be more confident the mean is there. So let's just run it again here with 99%. So we'll go back to our z-test, keep everything the same, but we'll bump this up to 0.99, calculate. And now just rounding to a whole number to make comparison easy here. So that lower limit will be 33, less than mu, less than 39. All right, so we can see the visual here that we've got a longer interval, so 33 to 39. And again, the point estimate didn't change. That was our 36. So to complete the sentence here, now it says, which interval is larger? So the 99% confidence interval is larger, because if you want to be more confident your interval contains the mean, we need to give people a larger range of possible values. So the 99% confidence interval is larger, since there must be more values in the interval to be more confident it contains the population mean than for the 90% confidence interval. Okay, so the summary here is just remember that higher confidence means larger intervals. All right, and next we will address questions where we are actually given the data. So just to end here, these 20 deliveries that they considered, all they told us was the sample mean. They didn't give us the times for each of the 20, and we'll take a look at those types of problems next.